Okay, so these are the procedures. So you want to really also, all the time, you want to have quality control for every step. So you want to start with your samples. You want to make sure that your samples, in terms of the time when it is obtained, whether it is fresh or if it is FFPE or if it is solid tumor, you want to enrich for your tumor. So our optimal minimally, we like really to get 30% of our analyzed samples being tumors, and the more tumors, the better off, but 30% is acceptable, and all our assays are validated for the solid tumor, validated on this. But for the hematology, it is, of course, completely different ball games. You have to take what you get. DNA and RNA isolation, you want to really look at the quality of your DNA and RNA, and especially for the RNA, you want to make sure you have intact RNA. You don't have degraded or too much degraded RNA. Then you do your library constructions, QC. You have to run QCs, multiple QCs. You do the sequencing, generate the BCL file. Then the BCL file converted into FASTQ and JSON file. The JSON file is a file that it is annotated of the FASTQ files. And you generate multiple things using different software. So the first software is actually used to generate the VCF file, which will give you the mutations, the list of a mutation in your sample. The BAM file is practically the structured images of your sequence, actually. You want to look at CMV, which means copy number variations. That's a different software. You have to use it in your pipeline. Splicing, you want to evaluate splicing. That's a different software in your pipeline. If you're looking at B-cell and T-cell clonality, you want to use a different software in your pipeline. If you're looking at viral RNA or DNA, you want to use a different software in your pipeline. For fusions, also different softwares. For TPM, which is quantification of the RNA, that's transcript per million. That's what TPM stands for. So you want to use a different software for that. We are interested in the HLA, so genotyping. It is a different software for that. Tumor mutation burden, we have to use a different software. Homologous recombination deficiency evaluation, that's also a different software. So it takes almost 24 hours and sometimes more than 24 hours to go, after you generate your data, to go through your multiple software. On top of that, actually, we have a different way of increasing the sensitivity and make sure we are not missing everything. So we have a list of hotspot mutations that we go straight to the FASTQ files and look for mutation in the FASTQ files, because sometimes the VCF files does not read the mutation very well. So we look for the hotspot mutation in it and we pull them out, and our technologists as well as pathologists have to compare the hotspot list in these patients. The other things, we developed another software in which we look at the mutation in the same run. So if we see a mutation, specific mutation in the same run in large number of cases, in 4 or 5 cases out of 100, we ask the question, is this artifact, something going on there? So all these are very important things. For the fusions, because you get a lot of garbage with the fusion as well. So we look for the hotspot fusions or the fusions at hot spot. And we pull them out actually from the FASTQ files if they are there. So we have software that we developed on top of the original things. So it is very complex if you want to really do it correctly. Do you guys understand? So generating the data is the simplest part, to be honest with you. Analyzing the data this is where the hard work starts. And this is actually, all this data go first to technologists. We have technologists, we train them, and it takes like 6 to 9 months to train them and clean up all these data. Then it goes to the pathologist, the pathologists have to go through all of this data again one more time and decide where to go from there. Absolutely.
Because, I mean, there will be many features that we don't know what is the goal.
Exactly right. As a matter of fact, there are so many, because you can imagine, we have a lot of pseudogenes, Pseudogenes, they can really, they have different sequence. And it is not unusual that the data, and especially with hybrid capture or any sequencing, all what it takes, maybe 10 nucleotide from the other genes to match. The software will give you that this is translocation, and it is not necessarily translocation, And there are some we see in normal individual, and these have some of these, they have been published in papers actually as if they are translocation, and definitely they are not translocation. We see them all the time. And the other things, which is also very complex and very difficult, is alternative splicing between two genes. So two genes next to each other, on the same chromosomes and next to each other, they can really have alternative splicing, and this is part of the complexity of the human, and perhaps biologically they are relevant, but we don't know. But we don't really call them as a translocation when it is alternative splicing, if they are close to each other, And this is why it is very important to have a list of the hot translocations that we look for. It makes it much more easier for the pathologists and for the technologists to pull them out, and our software will pull them out completely as separate and give us the option. And of course, we get the deletions that on the same chromosomes that could happen and lead to like the FIP1, L1 on chromosome 4 with PTGFR alpha in hypereosinophilic syndromes. That's again on the same chromosome. It is small deletions, but that's legitimate translocation, and we report it as translocation. So it is really very complex, and you have to be very careful.
Is there any effect on artifact formation in that when you do the clustering on the flow cell, or they're using to reduce the number of dyes, the color? Normal sequence is 2 colors.
Right. Today it's two colors. There were some problem, and most likely you are referring to indexing problem at sometimes which happened, and they fixed it, later on by using two indexes. But it's quite possible the technology and the chemistry generate artifact, no question about it. And this is why, in my opinion, you have to tailor your software for your own chemistry, for your own technologies, There are multiple companies out there tell you, oh, we have the pipeline for analysis. All what you need, you run it on your instrument and send us the data, and our pipeline can analyze the data for you. To me, it doesn't work this way, because, again, you have to make your pipeline, you have to train your pipeline for your own artifact. And make sure that your pipeline is specifically tailored for your own chemistry, for your own instrument. As you know, and you alluded to, Thermo Fisher will generate different artifacts from the Illumina, and I don't want to even talk or think about the complete genomic, what artifact it will generate. Yeah. So you have to be very careful, absolutely.